Another interesting question that the Greek knew the answer to is the question of whether there are infinitely many prime numbers or not. And they were able to answer this question, and they discovered that, in fact, yes, there are infinitely many prime numbers. As a matter of fact, we don't have the complete list either, even now, because there are infinitely many prime numbers. Euclid was one of the people to show us an answer to that, and it had a nice proof. But before I can show you the proof, I have to kind of go on a tangent and show a proposition is true so that we can be ready to prove that there are infinitely many prime numbers afterwards. The proposition basically is called proposition 4.7.3, and it says for any integer a and a prime p, if the prime p divides a, then it will not divide a plus 1. So for example, if a is 25 and p is 5, and I know that p in this case divides a. So in other terms, I know that 5 divides 25. Then this theorem guarantees that 5 will not divide 26. It will not happen. And this is true for any numbers a that is an integer and a number p that is prime, where p divides the a. This is a true statement, and I just demonstrated one quick example, but how do you go about proving the statement in general? Keep in mind that this is an if-then statement. So there's an if-then. So that means it's a conditional statement, which means it can be proven either directly, if you want, which is going to be very difficult in this case, or it could be done with a proof by contradiction or a proof by contrapositive. In this case, I am going to go with a proof by contradiction. So in other terms, I'm going to say suppose not, which means I want to suppose, for the sake of contradiction, that there is an integer a and a prime p, where p divides a and also p divides the next integer a plus 1. So even though this is an if-then statement, it's a conditional statement, I can still do a proof by contradiction. And this statement in blue right now that I'm writing should lead to a contradiction, which means that the original statement in the theorem must be then true. Let's see how this contradiction happens. Now, by definition of divisibility, since p divides a and p divides a plus 1, there must be integers k and t such that a is equal to p times t and a plus 1 is equal to p times k. So it follows that since a plus 1 is equal to pk, that we can do a substitution and replace a with pt. But this means that we can now move some terms around and have 1 is equal to p times k minus t by factoring. And again, k and t are both integers, so k minus t will still be an integer. This implies that there's a prime number that divides 1. Remember, since k minus t is an integer, then that means that p is a factor of 1. So there's a prime number out there that divides 1. But wait a minute, this is a contradiction because the only divisors of 1 are 1 and negative 1. And our prime numbers start with 2. They don't include 1 and negative 1. So this implies that our original assumption up on the very top at the very start of the problem must be a false assumption. Because by making that assumption, we get a contradiction, which implies that the statement in the theorem must be true. And that means we are finished.